We will see the construction of the Huffman tree with an example. Okay, how that binary tree is constructed and what would be its cost, everything we will see with an example. Okay. So, we continue with the same example. A has frequency 45, B 12, C 13, D 16, E 9, F 5. Okay, these are the frequencies. We will start with the nodes like this: A 45, B 12, and C 13, D 16, E 9, F 5. These are going to be the leaves anyway. So, let us start with them as independent nodes. Now, we are going to build a tree. For the final tree, all these things will be leaves. So, we are going to combine, all right. So, this is where the way in which you are going to combine is, we will put together, okay, nodes with least weight. So, take the two least weight nodes E and F. Now, you create a node with frequency, you call this as Z1, frequency will be 14, 9 plus 5 is 14, and that will have on the left the smaller one, let us say F with 5, sorry. F with 5 and E with 9. Now, I can discard these two. So, at this moment I have a tree, a small tree, and then 4 isolated nodes. Okay. I am considering only the nodes. The new one Z1 is called the super node, because it is the combination of the input nodes. Input nodes are one node per character with the frequency as its weight. So, pictorially you can see now I have 4 nodes and one super node. A super node is created by combining 2 nodes. 2 nodes or 2 super nodes, but it will always be created by. Now, the minimum, if you see here is 12, 13, 16, 14, these 2 are the minimum. I am going to combine these 2 and create the second super node Z2. Z2 is the next super node that will have 25 as its weight. It will have B12 to the left, C13 to the right, and these 2 are knocked. Okay. So, 2 nodes are knocked, 1 super node comes into picture. 2 nodes are knocked and 1 super node comes into picture. So, now you will have a mix of nodes and super nodes, and how many of them we will have? 4 of them. Earlier we had 6, we have removed 2 and brought Z1. So, that will be 5. Out of this 5 we removed 2 of them and brought Z2. 2 nodes are deleted, 1 node comes into picture. So, net reduction is 1. Now, if you see in this 45, 16, 25, 14, these 2 are minimum, they are the smaller ones. Combine them. Now, you create a super node Z3 with, add the weights, 16 and 14, this will be 30, and Z1 with 14, this will be on the left, D16 will be on the right. Of course, Z1 has got F and E on the left and right. These two are gone. Now these two have been merged. Here it is already there, Z3. Now you have 45, 25 and 30. 25 and 30 are to be combined. So create another super node Z4, and that will have the weight 55. That will have a weight 55. Let me write clearly with a big Z4 with weight 55. It will have Z2 with the 25 on the left, Z3 with the 30 on the right, 25 and 30, 50. This is gone. These two are knocked out. Of course, Z2, Z3 I did not repeat. I can show that in the next. Now there are only two. These two you combine. The minimum is these two are the minimum. So I will have an Z5 which will have A on the left, Z4 on the right. I will have Z5 with 100 with A 45 on the left, Z4 with 55 on the right. Z4 will have Z2 on the left and Z3 on the right, Z2 and Z3, Z2 that is 25, Z3 that is 30. Z2 has got the following. Look at what is Z2. Z2 has got B and C on the left and right. Z2 has got B12, C13 on the right. Z3 has got Z1. Where is Z3? You can see Z3, Z1 on the left, D on the right, Z1 on the left, D on the right. Z1 has got F on the left, E on the right. Now this is the complete tree. This is called the Huffman tree. Okay, this is called the Huffman tree. How Huffman tree is constructed? By combining two low weight nodes into a super node. And this process will be repeated precisely n minus 1 times. Therefore, there will be n minus 1 super nodes are created. Here in our example, there are 6 characters. You can see there are 5 super nodes, Z1, Z2, Z3. All super nodes we will label with Z. The original characters we will call them as A, B, C, D, E something like that, so that you clearly see the new nodes that are created by combining this. Now this is a full tree. In this tree you can see that the characters are all on the leaf. All the characters, your input characters are on the leaf. So going to the left is 0, going to the right is 1. Therefore A has code 0, B has code 1 0 0, C has 1 0 1, D has 1 1 1, E has 1 1 0 1, F has 1 1 0 0. This is the coding scheme. The coding scheme obtained by the process of Huffman tree is this. You see that a tree is constructed in a particular way, and after construction of the tree, from the tree you derive this. And what is the size of the file? Now you can see this is 45 times 1, that is 45, and B is 12, 12 times 3, 36, C is 13, 13 times 3, 39, D is 16 times 3 is 48, E is 9, sorry, E is 5, right, F is 9, sorry, let us check, I forgot what is the, E is 9 and F is 5, E is 9 and F is 5. So 9 times 4, this is E, 36, this is 5 times 4, that is 20. Only this many bits you will use. So you can see it is using only 224,000 bits. Fixed length code for A, B, C, D, E, F has used 300,000 bits, but this is using 224, about 75 less, about 25% less. Here is a variable length code. If you use this, it is going to result in a file which is smaller than the fixed length one. So there are several questions that we have. Is this optimal, or can I find some other tree with some other structure which gives a different coding scheme but with less weight or less cost? That is, if you use that coding scheme, the resulting binary file, can that be smaller? We are going to show that no, this is optimal. Okay? We are going to show that the code generated by the Huffman tree is optimal. So we will take a closer look at the Huffman tree construction, and then we will argue that the code generated by the Huffman tree is optimal. We will see the details in our next discussion. Okay? Thank you.